everyone. I'm Lori DeToro, Communications Manager for Turntide Technologies. Thank you for your patience waiting for us as we got our technical problems worked out this morning. And thank you for joining us today for the Current and Wave webinar discussing inverter selection and integration. We are pleased to have Turntide's Head of Product, Power Electronics, Chris Pearce, presenting today. Before we get started, as you know, we have some housekeeping tips to share. This presentation is being recorded and will be available on demand on the Current and Wave website. We will be taking questions at the end of the presentation, so please use the Q&A, not the chat section where you've been seeing my messages this morning. Use the Q&A section to ask your questions anytime during the webinar, and we will answer as many as possible. We have a couple links in the chat for you. The first is an inverter implementation guide. The other is our October webinar registration page. That webinar will discuss cybersecurity and functional safety. So go ahead and bookmark these and make sure you check them out before you log out of the session. Remember, this is a live event as proven this morning. And so when we mess up, and we probably will, laugh along with us. That's it for housekeeping, and we are ready to get started. Chris, take it away.
Hi, okay, thanks very much, Laurie. Sorry about the late start. So welcome to our Turntide webinar on inverter selection and integration. We're going to have a walk through some of our products, and we're going to talk about how we think about selecting inverters and what the task is there. So next slide, please. So we have a look at an overview of the Turntide technology and electrification legacy. Some of the key factors in terms of selecting an inverter, some of the motor control decisions that you'll make in selecting an inverter, voltage and current ratings of that system design that we would then impose on the inverter selection, integration of that inverter into your vehicle system, and then any other considerations we might have going forward. So and then we'll have some Q&A and hopefully an interesting conversation. But first of all, just introduction to Turntide. Some of the attendees might not be familiar with our legacy and origins. So Turntide is an amalgam of 4 companies. Turntide acquired Sevcon, Avid, and Hyperdrive in 2021, and has subsequently refocused its business activities entirely on electrification, building on these 3 great names in electrification. Sevcon, famous for electrification of milk floats and forklift trucks and electrified systems throughout the decades. Avid Technologies with their line in novel bespoke thermal products and axial flux machines, and Hyperdrive with the great use of the ASC Gen 1 batteries, and now our Gen 2 batteries are coming online. So these are part of the mainstay of the Turntide technologies, which we've integrated over the last 4 years. So who am I? My name's Chris Pearce. I'm the Head of Product for Power Electronics here at Turntide. I've been with Sevcon, Borg Warner, and now Turntide for 29 years now. Started off in Sevcon, and my expertise is around motor control, firmware, power electronics, systems, embedded systems, and functional safety. I'm really enthusiastic about this industry. It's kept me busy for many decades now, and it's always a good day to come to work. So thank you. So how do we choose an inverter? So inverter selection starts with a problem to solve, and that usually has got nothing to do with inverters. It's about the problem we're trying to solve, which is that something or somebody needs moving, and how much we're moving and in what direction. With respect to gravity is important, and how fast does it need to move. Once we've got to the bottom of that, we need to know how long we're going to move it for and how much energy is required instantaneously to make it move. And from that, we can then start to think about the power requirements on our inverter system and how much energy storage we're going to require. So the energy storage and the inverter interaction hinge around the DC link system voltage. This is directly related to the current that we're going to put into the motor to move our load and solve our problem. And there are two interrelated questions there about what our DC link system voltage needs to be. That decision is constrained by a number of things, such as existing batteries that you've got on the shelf in your production lines and systems, charging infrastructure, or you're starting from scratch and the world's your oyster, in which case you're choosing a higher voltage to minimize loss through heating, I2R losses, lighter cables, lower motor currents, or you're looking for a safer, easier to work with option, lower EMC requirements, but you're limited, around 800 amps of current with easily managed systems. Next slide, please. So assuming that we're talking about a vehicle system, some of the impacts of the motor selection on the inverter are the primary parameters for vehicle level attributes of gradability, rate of acceleration, maximum speed, cruising speed, and of course range, which is a critical factor in selecting and designing a electrification system. The maximum torque of the motor governs your gradability, which is directly linked to the amount of current you can get into the machine. Rate of acceleration directly related to how much power you can get out of your battery. Maximum speed related to the maximum output torque and maximum speed of your motor. So this is important from a field weakening view and maximum output frequency of the inverter, and cruising speed dictated via the continuous operating point of your inverter, the output current at which it will run forever. And obviously range is dictated by the way you drive. If you drive gently and slowly like a granny, you'll go a lot further than if you get the full performance out of your electric machine and give it all a welly. So that's an important dictation of features and functions in your inverter system to maximize range and performance options. Just a note here on some of the points about motor selection is around packaging the motor. Motors come in sort of all sorts of form factors. Are you going to be using liquid cooling, air cooling? Airflow around the power electronics is a critical part of that, and all constrained by cost of the final product. So here's a kind of use case for a typical use case of this sort of motor size here. We are considering the power in versus power out of the vehicle system. And if we consider the Newtonian physics of the entire train of battery to vehicle performance, we need to be considering things such as the curb weight of the vehicle, gear ratio, tire diameter, rolling resistance, etc. Once we have all of those parameters, we can feed those into various drive cycle profiles, which allow us to determine what the torque requirements on the motor is at the vehicle level to perform the task at hand, the maximum speed, the maximum gradability that we need, or if it's a pump, or if it's a lift or a crane, the physics are the same. Broadly speaking, ultimately it results in a motor torque, and at the end of the day, that motor torque is going to get turned into current of some amount. So if we look on the graph on the right here, here's a couple of drive cycles for a typical three-wheeler vehicle in the sort of 7 kilowatt range. We can see hill cycles, highway cycles, city cycles, and rural cycles all have a different profile. Each one of these dots on the screen represents 1 second of operation. So the concentration of dots on the screen gives us a clue as to how long how much the system is going to operate at those power points, and therefore what kind of ratings we need to come up with for our energy storage, inverter and motor system. And we can translate that torque directly into power. Power is a terrible way of sizing anything because it has two factors in it of either torque or speed or voltage and current. However, it does give you a chance to take a step back to view the system with one number instead of multi-dimensional problem. So here we can see the 7 kilowatt kind of average rating of this three-wheel application, and so we can start looking around 7 kilowatt type applications, whether it's 700 volt or 48 volt, that's still a choice to be made, but governs how much current we are going to be managing under those circumstances. So next slide, please, Laura. So that brings us on to, now we've quantified the problem we're trying to solve in terms of torque and speed and power. We can then start choosing motors which might meet that. Again, we haven't really decided on the voltage, but probably for a 7 kilowatt application, we're going to be on the lower voltage range because of charging infrastructure, safety concerns on the type of vehicle we're talking about. Typically, we're looking at interior permanent magnet or surface magnets. Interior magnets becoming very much more popular because of their increased torque density over surface magnet machines, but again, come with control problems that the inverter is going to have to deal with, which is more significant to extract the full torque available versus a surface permanent magnet machine, which is very simple to control. So there's a lot more thought has to go into the control algorithms in the inverter to extract that extra torque. Each permanent magnet machine comes with its own encoder type. There's a number of common on the market: sine, cos, resolver, UVW, ABZ are typical in the permanent magnet space. And then there's thermistor types. There's at least 5 or 6 common thermistor types, of which different circuits are required to get a good level of accuracy from. So important to match those with the inverter you're choosing to get a good thermal protection of the motor. It's important that we don't let the motor get too hot, and that's a critical function of the inverter. After it's putting the current into the motor, it needs to make sure it stops at some point. Position sensor is critical for good, robust control in traction applications. Sensorless is not really a thing in primary traction control because of its propensity to fail. So it's important to have the right encoder and that the encoder interface on the inverter is correct. Induction machines still around, still quite popular in the market because of their robustness and cost effectiveness. They're much larger and typically use AB encoders. So the integration of the motor, the DC link selection, a good pairing, and the inverter selection is going to dictate a lot of the success of the end application. So here's a quick overview of the inverters we've got in front of me. This table represents our current range of options for different applications at different voltages. We have a low voltage range of inverters, which up to 135 volts non-operational voltage on the DC link, peaking at maximum about 60 kilowatts with a continuous rating of about 20 kilowatts in the form factors we have. And our Gen 5 size 9 range is a workhorse at 350 in the 150 kilowatt for 2 minutes, 80 kilowatt continuous range, and a 700 volt option at the 40 kilowatt, 20 kilowatt continuous operation, which is great for 700 volt applications looking for small ancillary support for pumps and fans on a larger vehicle system. So another important part of the inverter selection is its voltage rating and how it manages the voltage across the range of charge of the selected battery. So here's an example of how our Gen 6 product would manage a 25S LFP battery, which is about 2.5 volts per cell. It gives us an 80 volt nominal battery, but we can see when that comes off charge, it's going to be at 91.3 volts. So it's important that the vehicle can drive straight away. And at 100% SOC, we want to be making sure that the product is available of delivering full torque. So the blue lines represent the torque cutback profile, which protects the battery from excess discharge according to basic voltage availability on the DC link. We need to keep some headroom for protecting the inverter from over voltage. And this derate system is fully configurable, should be configurable in your chosen inverter, and you can select the DC link gain cutback according to the profile that the battery requires. Okay. So back to our previous example in terms of current rating considerations now, inverters typically specify a peak overload rating and a continuous rating. The continuous rating is the 1 hour rating at which, with the right heat sinking, the product will operate and output current continually. So for instance, on the right here, we have the Gen 6 size 4 profile with a given motor of that outputs a maximum torque at 350 amps. Continuous operation for that product for an indefinite period with the right cooling would be at 190 amps. So you can see how that the majority of the long duration activities of that system, which will be the highway cycle, city cycle, and rural cycle. So that's, you can see that the highway cycle there is on the right hand side, going up to nearly 9,500 RPM. So that's the high speed driving. So it will do that indefinitely. The city cycle driving around the town, and rural cycles are all under the continuous operating range of 190 amps. And the hill climb and the difficult, challenging operation is only for a short amount of time, indicated by the fewer number of dots there above the 190 amp line. So above the 190 amp line there, in any one given drivability profile, we've got 120 dots worth of operation before the system is going to get overly hot if you're at the full 450 amps of the product. In the Gen 6 size 4. Obviously, the less current you ask for, the longer you get. And there are simulations we can run based on the heat sinking size and duration of current to determine the length of operation at each of those operating points, but above the continuous rating. So the right motor, and it has to be paired correctly. So with an interior permanent magnet machine, which has a high torque density, we need to do a lot of careful analysis of the operation of that machine across its torque speed range. That gives a set of results and torque accuracies that we can then use to, whilst we're doing that, measure the system efficiency. The system efficiency is going to give us the range that we're looking for in the vehicle system, and the torque accuracy of that product is going to make sure that we are meeting the design of the vehicle system, maximizing the amount of cost of the drivetrain against the performance of the vehicle, right size of the system, and makes it more attractive for your end customer to buy. Efficiency is all about the range. So the more efficient the system is, the further it's going to go, and that's differentiator in terms of the total cost of ownership, as the battery is the most expensive part of the vehicle system. We need to minimize the amount of battery and maximize the amount of range through efficient driving of the motor at the very lowest level. So we've picked our motor, we've picked our inverter, we have a DC link voltage defined. We think we're going to meet the requirements of our design which solves our problem. But now we need to have a think about the features and functions which are required to actually control the torque in the machine at the right required time. There are a couple of architectural decisions to think about here, whether that is a centrally controlled system via a VCU, or whether you want the inverter to do all of the work and calculations. You are likely to be taking in switches from a user or an automated system over CAN probably, or via switches, potentiometers, and other input devices. That could be done into a remote unit and sent to us as a talk demand, or the talk command can be calculated on board. There are also considerations regarding isolation of the system and how your I/O switches in terms of either to 12 volts or battery voltage, and these kind of architectural constraints that have to be considered when selecting your inverter. So dialing this across to one of our inverters we've got in front of us, which is the Gen 6. Just a quick run through of some of the options here. This is the extended version of the Gen 6, which is an isolated battery switched architecture, which allows us to operate an isolated system for the higher voltages of 80 volt, 96 and 110 volts. So all of the switch inputs on this product are switched to 12 volts, and there's a 12 volt supply separate to the primary traction battery, which you can see on your left of the main block diagram. And this product can be used in a number of ways. It can be driven as a CAN, auxiliary CAN torque actuator via CAN, using a standardized control protocol, which we call H protocol. That allows us to set points of torque, DC link current limits for driving and braking, torque limits for driving and braking. Previous slide, please, Laura. Speed limits, torque limits, battery current limits, and voltage limits. So that's all available over the CAN bus. We can control the system according to a slave system, or we can set those parameters locally using a vehicle control system. We've got a powerful mechanism to customize the reception of CAN messages and use those in many different ways to feed parameters within the control system, or we can independently interface to Turntide user code, which allows a user to control parameters of the motor control at runtime based on CAN messages received or I/O states that can affect things like the maximum DC link current, maximum motor speed for different drivability profiles. We can then start thinking about setting up economy modes to limit ramp rates of torque, maximum speed, and reduce DC link current consumption, which all go towards increasing range, or implement interlocks, immobilizer functions, or any kind of user function that is bespoke and unique to your application. That's available via user code. And we've got many ways of being very flexible to meet the requirements of many different applications, including different motor types and switching motor types in and out via programmable logic. Just a quick overview of the I/O available on this Gen 6 product is available on the top left here. So we've got a multitude of I/O for the kind of controls we might need, PWM inputs and outputs for controlling of fans, high current low side drivers for controlling contactors like line contactors or pump contactors, low current drivers for relays, high side drivers to control inputs on auxiliary equipment like DC-DC converters and OBDs, etc. And a range of encoders we support depending on the motor selected for the application we're trying to solve. So just a little deeper dive into some of the sensors that we might see. So motor thermistors, we've got dual input motor thermistors, which we can use to cross-check for safety. Dual channel throttles with full plausibility check on both channels and redundant fallback on a single channel. We support 3-wire pots, 2-wire pots, and so the options for configurable system support is very flexible. Wire off detection on all of the analog inputs, and is a critical part of system design in terms of the functional safety, even at a very first level. So there's many options in terms of the I/O architecture and considerations there as well. And so this is an application we were working on earlier in the year, which highlights all of the features we've discussed, from motor integration. This was an induction machine, 60 Newton meter, 18 kilowatt induction machine. To drive this last mile vehicle, we were integrating the Gen 6 platform into this vehicle, into an application space which requires specific and bespoke CAN interface with unique controls, as well as some of the controls we've already specified in terms of dual channel throttle, foot brakes, and direction switches, as well as interfacing to VCUs and OBDs. So the challenge for this product is obviously it's a commercial vehicle grade 16750 type sprung mass type environmental demand, in that the environmental demands of this application are quite challenging, which the Gen 6 product here in front of me meets. And ultimately we met the goal of integrating this system onto the truck by exploiting the powerful features we're providing to ultimately provide a functional solution for this OEM. So that's a quick whistle-stop tour of the capability of the products. So we've got them in front of us here. It's much more fun to talk about them than to actually look at them. But the products I referenced here are the HVLP. This is the 700 volt, 20 kilowatt water-cooled system. It uses the Tyco connectors here, and it's very compact for the application at a high voltage, much more suited for the hotel loads, pumps, fans, and compressors. So this here is the Gen 6 product. Well, this is actually Gen 5 size 9. There's a Gen 6 size 9 which we're now going into production with, which has ASIL-C capability. This is a 150 kilowatt peak water-cooled system, which is compliant to ASIL-C specifications for a number of safety goals surrounding automotive, avoid unintended acceleration type goals. There is I/O on this 48-way connector for similar kind of applications that we saw on the slide earlier, and that is a great product here. So here's some typical motors that we might have chosen from. So this is a 7 kilowatt. This is 400 kilowatt, 200 volt. What kilowatt is that? This is about 10 kilowatts. And this is our AF143, which is about 80 kilowatt continuous. These motor products are all paired with these products accordingly, the inverters. So having a pre-paired motor with your inverter helps you select your inverter, and that solves the problem of getting that whole pairing done. So we're looking to offer as many pre-paired motors as possible. Turntide products paired with all of the Turntide products, so that's an integrated solution. Our Gen 6 and Gen 4 products are paired with a number of partner products, which via contact with us we can talk to you about. And this is a comparison of the Gen 4 size 6 and the Gen 6 size 6 product. These are both 650 amps, 550 amps at 80 volts. And this is a 600 amp peak 10 second, and this is 540 peak for 10 seconds. So you can see the advancement there we have made in terms of power density. But they're both great products. This one offers the configurability and user code that we were talking about. All of the interfaces to the motor position sensor, motor temperature sensor are all done via the AmpSeal 35 way. That's as a consistent connector to the previous Gen 4 system. And the same for all of these products. This is a multi-purpose connector for user I/O at the vehicle level, and also the motor thermistor and motor position interfaces are made via the same single connector. This product has all of the power connector interfaces on the same should have had a screwdriver, shouldn't I? On the same interface, and this lid, because this is a 400 volt product, has a HVIL interface as well, which when we take this lid off to reveal the motor connectors underneath, sets off a HVIL connection, which notifies the vehicle system that there's a safety cover removed. Not such a problem on the lower voltage systems, but again, this 700 volt has HVIL on both the DC and AC connectors here. And the two high voltage products here are water cooled, so that's a 50-50 glycol water mix with a defined flow rate of about 8 litres a minute, I think. And that's it really. So this mounts is a flexible mounting. The cables all on a single face allow you to mount the cables all in a unique, in a concentric direction. So we can slide that into a relatively confined space. A new feature for the low voltage product here is IPXXB finger guard, which allows us to protect fingers from what is now considered unsafe high voltage above 60 volts, which wasn't a consideration in the days of Gen 4 so much. Let me just whip this off just to see what's underneath. I did these up too much. Oh, Laura did anyway. Thanks, Laura. So same M8 motor lug connections here. We've got cable guides here to keep the cables running nicely in and out of the product. Dual direction finger guard here. So we've got all out on one side or all out on the other side, with a cable entry here. There's another version of this finger guard where it's 3 in, 2 out, so you can have a flow through arrangement as opposed to all on one side type arrangement. So the heat sinking for these products is all managed through the base plate, and so this is left really for the vehicle integrator to mount onto a metal vehicle chassis or heat sink, depending on what the thermal requirements are, whether it's a finned heat sink, passively cooled or forced air cooled heat sink. And these grid lines here allow the thermal paste, which is a critical part of an air cooled system, to spread evenly under there. And the same system is available on the Gen 4 size 6. So you'll see the same grid lines. These are features to allow thermal paste to be spread efficiently when we're bolting it down. So what else is there to say? I think that's covered most of the key features of the physical features of the products. Obviously, the products are complex in terms that they are doing motor control, I/O management, CAN management, thermal protection of themselves. There's a lot going on and a lot to think about in selecting your inverter for a given application. And here at Turntide, we've been doing it for many years now, and it's always an interesting problem to try and integrate an inverter into a new problem space, and it's what keeps us going. So I think we're probably open to some questions.
Sounds great. Thank you so much for the great presentation, Chris. As we begin taking questions, please continue to ask more if you have them. We'll get to as many as we can. If we don't get to your question, we will post a Q&A blog with the answers. And we are going to probably have a little bit of an echo, so we apologize for that. The first question is for CAN communication. Is there a permanent built-in 120 ohm resistor, or is it optional?
Is there an integrated 120 ohm resistor? Yes, there is. So all of these products have an integrated and selectable termination resistor. That is a standard option across the range. Yes.
Excellent. So the next question, and this is probably a little involved. What is involved with pairing a motor and a controller, for example, from different manufacturers? Because you discussed our partnering with different manufacturers.
So pairing is can be a complicated business, or it can be a relatively simple business. It depends on the level of torque accuracy and motor performance you want to extract from the machine versus the amount of time you want to spend on it. So increasingly, we're involved with very cost-sensitive markets, and customers are becoming much more demanding about how much power we get out of a given motor, and that kind of dictates how much effort you have to spend on it. And also, another aspect is the type of motor. So, as I said, interior permanent magnet motors are substantially more difficult to get the full performance out of. So, let's assume we're talking about that. That requires some work on the dyno, where we can spin the motor and inject current into the motor under controlled conditions into what we call the D-axis and Q-axis. And by doing that, we can evaluate what the internal electromagnetic design of the machine looks like. And once we've got that mapped out accurately, we can then extrapolate tables from that, which allow us to control the motor under all voltages and speeds. So that's broadly how we do it. There are simpler ways of doing it. There are methods we like to call like geometric mode, which kind of models some of that behavior to about 80% of the total performance available. And it depends on how reliable that is on the design of the machine.
Excellent. The next question we have is on slide 12 of the presentation, and Laura, on your computer, you may need to go to slide 12. What did the different graphs indicate and represent?
Good question. So the graphs here on the right here are system efficiency, motor efficiency, and inverter efficiency. So the system efficiency here is that right? Is that the right? I thought it was 8, was it? No, must have been 12.
They asked for slide 12.
If this is the right graph, this is system efficiency, motor efficiency, and controller efficiency. So system efficiency is the top graph is the product of the bottom two. So the overall efficiency of the system is governed by the system efficiency. That is how much loss we get between the battery and the motor shaft torque. So here we can see the dark green is above 90% system efficiency. And we can see the broad chunk of that is actually the motor. the inverters generally are pretty efficient, and certainly our inverters are north of 95–96% efficient in most operating points. The middle graph here we can see has got a lot more green, lighter green going to red, where the efficiency falls off. Motors become substantially less efficient at higher torques and lower speeds. So as we approach 0 speed at high torque, that's when they become really, really horribly inefficient. So those rapid launches from 0 speed, climbing hills, crawling around with a massive load, they're really horribly inefficient. And you really, if you're going to be doing a lot of that, you want to have a gearbox in there to get that motor speed up into a much more efficient operating point.
Great. And our next question is there a specific parameter that is needed for selection or integration that many partners do not have readily available that they should?
Feels like a loaded question. I think, generally speaking, there's always lots of parameters that we are either guessing about or making assumptions about, typically around things like maximum torque, what the duty cycle is. What is the duty cycle of the application is a question that often is very challenging to answer. Here I've shown examples of duty cycle from an OEM who really understand their application very well. Sometimes we don't have that luxury of really understanding how the end user is going to use the product. How long is it going to be spending climbing a hill, stirring thick tar at maximum current or whatever it is, versus how we've sized the system to deliver that. So that's probably the most difficult thing for anyone to answer, is really what the duty cycle of a given application is. I would say is probably the hardest question to answer.
Excellent. We have
That's a
one
question
more.
I would ask anyone asking me the question, and often the answer is a bit vague.
Excellent. So here is another question. Would it ever be possible, perhaps with AI, for an inverter to automatically learn a motor's characteristics, so no initial pairing would be required, thus allowing future upgrades in motors in the field? Is this a direction that is being evaluated? Of course, this is forward-looking, but an interesting question.
Yeah, really good question. Yes, definitely. It's definitely something that can be done. And it's something we are evaluating at the moment in terms of certainly getting a good level of performance from interior permanent magnet machines. That gets you most of the way. It's always going to be very difficult when you're dealing with non-linear systems. Machine learning and that sort of thing could help. And as those sorts of microcontrollers and hardware get cheaper and more well understood, there probably is a world where we could probably learn our way to the non-linear behaviors of electric machines. It would have to be something along those lines. Yeah, I can see that happening. I think that's probably definitely something that we'll see over the next 5 years or so.
The next question is, I'm familiar with the DVT for the Gen 4s and 5s, but what software is used to program the Gen 6 product line?
So the DVT is a classic bit of software, and interestingly, as an anecdote, that was one of my first jobs on the Gen 4 development, was actually working and developing the DVT. So I have a very soft spot for it. It's not a great piece of software. It was never intended for production use, but it is found its place in many people's hearts for all of its foibles and quirks. We have replaced DVT with a new software called CMC. It's designed from the ground up to try and solve the problems that DVT created, in that DVT is not very user-friendly. It's not very linear in terms of how it's laid out. It doesn't really lead you through the process. It doesn't allow you to try and integrate a product quickly and effectively. It requires quite a steep learning curve. So with CMC, we tried to decouple the intimate knowledge of CAN open and software architecture that DVT kind of requires to something a bit more focused on the end user, so that that process becomes a more linear. This is my motor, this is my AO setup, this is me setting up my drivability, and this is me driving the vehicle around and tuning it up. So the new product called CMC, which is now available with Gen 6, is focused on that. It's still got a journey. I mean, DVT is very old and has seen a lot of development and enhancement over the years. It's got a lot of customer feedback inside it. So today it is a powerful tool once you know how to use it. We're working towards that with CMC. CMC is also on that journey, but it's got much more user focus to it in terms of being able to select pre-paired motors, much more useful online help, much more intuitive flow to how you get a vehicle set up. So no, we are moving towards a product called CMC.
Excellent. Well, that is our last question, and I appreciate you all joining us today. Thanks again, Chris, for the informative presentation. This webinar will be available on demand in about 48 hours. We hope you'll join us for our October webinar, and we hope you have a great week. Thanks again for joining us.
Thank you very much.